Okay, problem 2 from exam number 3 shows you a pulley, mass hanging from it, while you're pulling a rope horizontally on the left side of the pulley with a constant tension TL. You're given the mass of the pulley, you're given the radius of the pulley, you're told all the mass is concentrated at the rim, and this block is hanging, that's hanging has a mass M, as opposed to the mass M sub P of the pulley. Okay, and the first thing you're told to do is to draw the free body diagrams for the system. And there are two objects in the system, the pulley and the mass, two objects that we need to worry about. So let's start with the hanging mass, M. Okay, and let's pick a positive direction. Since we're told that it's accelerating upward, I think the wisest choice is obviously we'll pick plus Y upward. And while we're at it, let me go ahead and write an X and say this is a right-handed coordinate system, so X cross Y gives us positive Z out of the board towards you, because that could be handy when we go to torques. So in any case, the forces acting on the mass M are a tension right, which has to be different than the tension on the left side. Otherwise, you can't accelerate a pulley if you have the same force acting on both sides of the pulley, now that we have massive pulleys. And so, yeah, the force acting on M is mg down. So that's it for M. Now when we look at the pulley, you're told you can ignore the forces holding the pulley in place, the forces on the axle. So all we really care about for this problem is the tension on the right, which acts to pull this point down, but actually acts to accelerate the pulley in the direction given by the right-hand rule, which would be into the page. R will be your moment arm. These two are perpendicular. And so this will give you a negative Z angular acceleration, whereas the force pulling to the left that you're pulling with, okay, will give you R, which is again perpendicular to TL. So R cross F will be a torque out of the page towards you. So let me just make some of that explicit. So the angular acceleration direction will have positive being plus Z hat for alpha. The angular acceleration vector, or out of the page. Or another way of thinking about it would be that this sense for positive angular acceleration corresponds to rotation in this direction. But remember, this isn't a direction for an angular acceleration. Okay, this is plus Z hat. Okay, and this again ignores the forces. If you are interested, what are the other forces involved? Well, you actually have gravity pulling the pulley down, mpg. You have some normal force from the support holding the pulley in place, but you also have TR. So the sums of the forces in the y direction would be N minus mpg minus TR if I'd asked you to solve for the normal force from the pulley once you know TR, but don't need any of that for the questions you're asked in this problem. And so you were invited to ignore that and to ignore these two forces when you draw the free body diagram. Okay, so that's part A. Part B says, we have actually already done part B, what's the direction of the angular acceleration of the pulley? Given that this mass is accelerating upward, that means the pulley is rotating in this sense, which is not a direction for alpha, and it's rotating faster and faster in this sense. And so omega will be from the right-hand roll, curl your fingers around up out of the page towards you. But not only that, the change in omega, that vector upward out of the page towards you, keeps getting bigger and bigger. So alpha is out of the page towards you, or plus Z hat with the coordinate system I defined here, or just say out of the page. And add towards you if you want. And any of these should work and earn you full credit. What won't work is this. That counterclockwise direction is useful to think about, but it doesn't actually define a unique direction for alpha. So you'll lose a point if that's your answer. Okay, so part C, again, asks you something that's relatively straightforward. what's the relationship between the magnitude of the angular acceleration and the linear of the pulley and the linear acceleration of the block. And you could just write this down if you wanted, and you should receive full credit. A equals alpha r. And these are magnitudes for A and alpha. And that's from the formula sheet. Formula sheet if you want. And if you want to derive that from something more basic, you would say, well, for any circle, the arc length is theta measured in radians times r. Take a time derivative, and you would have the velocity equals omega, angular velocity times r. Take another time derivative, you'd have A equals alpha r. But this is all you needed. D says, okay, write out Newton's laws for the block and for the pulley in terms of the quantities that you're given above, plus the things that we'll end up solving for, the tension in the right side of the rope and the A and alpha for the block and pulley. Okay, so for the block, we just have to write down the sums of the forces in the y direction equals mass times acceleration, which is in the y direction. And that just goes to TR, which is positive for us, minus mg equals ma. I'll call that equation 1. That's half of what you need for this problem. And now for the pulley, we have to write down the sums of the torques equals I alpha. Okay, and so that becomes TL times R. That's positive, remember. TL, R, you do R first, cross it with T, and that gives you a vector out of the page towards you, which I defined as my positive direction, to correspond with the positive A going upwards. Okay, so TLR minus TR times R, remember R is the moment arm, which is also the radius of the pulley, equals IP alpha. But you weren't given IP. We have to convert that into things that we were given, but we're told that this is a pulley with most of its mass on the rim. So I pulley is just equal to the mass of the pulley times R squared. And you're supposed to know that or be able to figure it out easily. And while I'm at it and simplifying this expression, I'm going to also use alpha equals A over R and plug both of these into this expression. So what I have then is TLR minus TRR equals MP R squared times A over R. This squared cancels that. All the R's cancel. And we're left with TL minus TR equals M, mass of the pulley, times A. That'll be my equation 2 that I'll need to move to the next part of the problem and solve for. And solve for everything. Sorry, I didn't have that visible. Okay, so now let's continue with part E. So part E says, okay, now go ahead and solve these two equations for the tension in the right part of the string and the acceleration of the block as it accelerates upwards. Okay, so you look at these two expressions and you see how can you simplify them. Well, TR appears as plus here and minus there. So if I just add equation 1 plus equation 2, I'll end up eliminating R and just have an expression with known quantities in A. So that's all I need to do. So that leaves me with TL minus TR plus TR cancels, minus MG equals M plus MP times A. And I could just rewrite this for the acceleration A, divide both sides by M plus MP. So the acceleration is TL minus mg divided by m plus the mass of the pulley. Got the acceleration. Once I've got that, I look at these two equations. I can substitute into either one, but the one I'd like to substitute into is this one because that's simpler. I can write this for TR pretty easily. Okay. So equation 2 can be rewritten as TR equals m plus or m times A plus mg. Okay, and with that I can substitute in for A Oh, by the way, this is, yeah, that's right. M times quantity of TL minus mg divided by m plus mp plus mg. Okay, and so well, that's a reasonable answer right there. There's another thing you could do. You could substitute a into this expression. That's how I've done it on the written solutions, because you know TL, but both expressions will end up being equivalent. Okay, so this is the tension in the right side of the string. And then to check my answers for reasonableness, what I want to do is put in and you're required to do in part F, is to say, well, if you set TL equal to mg, in fact, what you're doing, if you set TL equal to mg, you're just balancing the force of gravity. And so this thing, well, if it wasn't moving, it would remain at rest. It could move at constant velocity, but it's probably easiest to think of it as remaining at rest if you just pull with TL equal to the weight of the mass. So that should give us zero acceleration. And in fact, when you go to our acceleration formula up here, okay, if TL equals to mg, we have mg minus mg divided by m plus mp, and that's equal to 0. And as I just explained, that makes sense because you're just balancing the weight with the tension that you're using, applying to the pulley. So really the pulley just changes the direction of the tension. You could just be holding it straight up and have the same answer. Okay, so what's the tension on the right side of the string? If you do this, well, do I even have to write it out? If you have TL equal to mg, then you have mg minus mg. So this goes to 0, and you're left with the tension on the right equals mg. Again, just as we said, if there's no acceleration of the block, no angular acceleration of the pulley, okay, then the tensions on the left and right are the same. That's equal to TL, and that again makes sense. So we're done.